Hello everyone, welcome to Gyandeep, a channel where you get to know everything about data science. Okay, so a very quick recap of what we have done so far. We started by building a quick understanding of the NER and RE. Then we went about doing the data labeling using Label Editor or Label Studio rather. And then we had the code discussions essentially revolving around the custom NER model using Stacy and the Stacy Transformers pipeline. In the previous video, we covered the bio-tagging, we had a code discussion, and we learned how to convert the Label Studio annotated data into the bio format. Now we'll be using this data to essentially train a custom NER model, and we'll have the discussion around it in this particular video. Okay, so let's get into the code part of it. So in the previous video, we used this notebook and we'll extend this further in this session as well. So we started by importing these libraries. We talked about biolabeling for NER, right? And we essentially got the bio tags, label underscore studio annotated JSON. This was the name of the JSON file, and we performed this particular step to essentially get the data in this format where we had the text and all the entities here, right? And them being in the form of a list. Then we took out all the existing labels from the JSON file. So we created existing labels where we appended all the labels, right? And we also created label dict to essentially look up for the tags to which these labels actually belong to, or text actually belongs to. For that, we had created this function, and so for example, if we have get underscore val international atomic energy, we were getting org as the token class or the tag, right? And then we took this step essentially to get the data in the bio format. If you have not seen the previous video, I encourage you to do that. Okay, now let's get into building the transformer model. These are the several of the libraries which we'll be using. The most important one being the transformer. We'll be also importing BERT tokenizer, BERT model, and we'll be using get linear schedule with warm up. Then we'll make use of label encoder. So essentially to encode the classes, the token classes that we have here. And then some of the standard imports we'll be importing torch, then the NN module from here, from sklearn, we'll get the accuracy score, train test split, right? And so on. From torch.utils.data, we'll also import data loader. Okay, so the very next step is to get the data in the PDF format, and so that's where these steps are involved. So we essentially iterated over the range of len talks. Talks is essentially all the tokens. Okay, so yeah, the sentences actually undergone word underscore tokenize, and they would be giving us these tokens, and then the list is created. Okay, so we'll be essentially getting a list with the sentence number and the corresponding tokens and the corresponding labels. So that's what is happening in this step, and we'll convert it into the data frame format. So we have sentence number, word, and the corresponding tag here. So all fine till this step, and let's see how is the distribution looking like. So for our data, if you see there are these many tags, and the number of items for each of the tags is very limited. So for blog alone, we have 38 entries. For the rest, it's very, very minimal. So what we'll do is we'll essentially remove the other tags and we'll just confine ourselves to finding the B lock. So it will be a two-class classification, getting the B lock and the O tags. So that's what is done here. Let's quickly check this. So we have O now as 425, B lock is 38. Okay. Next, we'll convert these labels or encode these labels. So we do a label encoder here. Then we'll group by these sentences and essentially aggregate by word and the tag. So we get these into the list format. So we have the list of the tokens and list of the tags, corresponding tags. Okay, we'll do the train test split here and we'll essentially reset the index. So my train sent, if we see, it looks something like this. So the German form works as a subcontractor, etc., etc. These are my tokens. The corresponding tag actually looks like this. So 10 German probably got identified as block and that's why a 0 here. Okay, next we'll define the config. So we need to add the two special tokens here, the CLS token and the separator token in my text data, and we'll be adding value underscore token in my the values or the tags data. Right? In the case of tags, we'll have the value underscore token preceding it. Okay, and the max length to which we'll be actually working on, max length of the text is set to be 128. We have very small data, so we'll confine in our batch size for train and validation both to be 2. We'll run it for 10 epochs. We'll use the BERT tokenizer. We'll be essentially using BERT base uncased. Okay, next we create a dataset class. Here, we start by defining the init, and the self-taught text essentially gets all the text, and the tags are in the self-taught tags. We get the length of all the items under my data set by doing def len self, and that actually should return len of self dot text. So essentially we count the number of the text that we have in our data. Okay, then we get the item. So we iterate it over the individual row item of my train data or validation data, whatever the case might be. So here we get define the get item, and text is essentially the index that we pass here, and tags is again the tags index, whatever is the index passed. So this will iterate over the entire set or list of entire set of the items. Okay, we'll then create the empty list as the placeholders for the IDS and the target tag. Okay, and here we see that we have done an enumerate over the text. We get the individual text from in the form of a variable called s, and we essentially will encode the tokenize and then encode this s, right? So we'll do an add special tokens as false because we'll be manually doing it in the coming steps. So we get the inputs here, config dot tokenizer dot encode, and then we will get the lengths of the inputs. So essentially length of the encoded part that we encoded tokens that we got from here for the text called s. Now we'll extend the IDS and it will contain all the inputs. So all these encoded items will be there. Now the target tag, the corresponding target tag for that will be again doing an extend, and it will be essentially the length of the input here, len input len, which is len of inputs, and the tags I, right? So we will fetch the value of the corresponding tag and will have it multiplied. So it will get multiplied. We'll get a list with the length of inputs and containing the tag elements, a tag element which is essentially defined by tags I, this I. Now, this is what we get under target, and this we will iterate over on the entire text, right? So for all the tokens, we'll get the corresponding inputs and the target tag. Now it's the time to add the special tokens. Now we are supposed to be adding the CLS and token and also the separator token. So we will essentially be deducting 2 from the max length. So my IDS, the max length of the IDS will be config.max length minus 2, right? So we'll deduct 2 from here. Similarly for target tag, again the max length, it will go till max length minus 2, okay? And then we will be manually adding the special token. So in case of IDS, we'll be doing a config.cls. So we added a CLS token here, and which is 101 here, right? 101, and then we get all the IDS, and then we have the separator token, which is 102 here. Next, for the target tags, we again get the config dot value token. So it's a zero token, and then followed by all the target tag, and then again we have the config dot value token. So it will start with zero. Okay, and this list will be starting with zero. Will contain the target tag, all the elements of target tag, and then it will end with again a zero. We'll create a mask which is now which essentially be just containing a single element with a numeric value of 1, and it will extend till the length of the IDS. And similarly token type IDs will create with an element called 0, element value of 0, and it will also extend till the length of the IDS. Now we need to be providing the padding, so it extends to the max length that we have defined. So we'll get the padding length. So this one would be config.max length minus len IDS. So for a particular sentence, whatever is my now len IDS, okay, we are dealing with single sentence here. So it will give me the len IDS as the will be essentially the length of the sentence, right? And then we'll deduct it this length from the max length, which happens to be 128 that we defined earlier, and then we would essentially append the zero values to the extent of this padding length. So whatever is the shortfall, say my length of the sentence is 30, then 128 minus 30 is 98. So we'll have the 98 of the zeros appended to IDS. Similarly, for the target tags, we'll have the 0 appended, right? So till the for the length of the padding underscore length, right? And then we'll have the mask. So mask would be again we had the one, so that's where the attention was required. So we had created this one for the len of IDS, and for the remaining part we'll be having zero been extended. Token type IDs, again, we had 0 here, and for the remaining part, we'll have the 0 plus into the padding length. So this essentially would all be 0 only. We'll return the 4 different things: IDs, mask, token type IDs, and the target tags. Okay, so now we will look for the device. Okay, so essentially it could be CUDA, or if we have it available, or the CPU. So that's what we see there. Okay, so next we'll write the train function. What we need for training, we need the data loader, the model. Okay, so what data I load, then the model architecture through which I fit this data, the optimizer through which I need to pass, and it will also include the components of loss and scheduler. Then I need to know whether I am sending it to the GPU or the CPU, and then finally we have the scheduler. Okay, we'll set the model to the train mode. So model dot train, and then we start with the loss at zero value, and we will keep on adding the loss for each of the iteration. So we next do the data in TQTM for I comma j in data to items. We send the data to the device. We do a back propagation here. So these are the back propagation steps. We calculate the loss during the training part of the model. Similarly, while doing the validation, we will be essentially setting the model to eval mode, model.eval, start with the loss at zero, right? And then we again calculate the evaluation loss here. Okay, so then we create the model. So we create a class called NER BERT model and then dot module. Okay, and in this, it will essentially inherit the NER BERT model, right? And we need to pass on the number of the tags for which the classification has to happen. So we'll pass that value here, num underscore tag, and in this case, the model is essentially BERT model dot. This is the pre-trained model that we are going to use, and we'll define the drop and in each of the layers. And so nn dot dropout is zero point 0.3, output is nn dot linear 768, and self dot numtag. We can have it. So this is the fully connected layer. Now only one fully connected layer that we have. Next, we'll have the forward propagation or the forward step here. So where we essentially take the model self dot BERT, and then we pass the IDs, attention mask, token type IDs, and we want to get a DIT. So we have set that to be false. And then for each of the steps, we'll have the self-taught bird drop. So essentially the dropouts. And finally, the out tag, the fully connected layer is what we have provided here. So that will give me the tag, right? Once we have the fully connected layer there. And in these steps, we essentially define the loss, which is the nn dot cross entropy loss, and we essentially define this function to get the loss value. So essentially, my NER BERT model will give me the corresponding tag and the loss values. It will return me the same. Next, we create the data set. Okay, so my train data set and the validation data set, right? And then we need to have it in the format in which the torch will be accepting, right? And we also need to define the batch size for my data loading purposes. Okay, so we have defined the same here, train underscore data loader and data loader class, and we have train data set and batch size is config dot train batch size, and in case of validation, it's the validation batch size. Okay, so now let's look into the model architecture. So numtag. So as we remember, the model essentially takes number of the tags here, right? Num tag. Okay, so essentially this num tag is the len of data dot tag dot value count. So here we just have it as 2, right? Okay, so then we pass this num tag to NER BERT model, and then we pass the model to the device. In this case, in this being the GPU, I am running GPU P100. Okay, so let's see how the model summary looks like. So here we are having the model summary. So maybe we can go through it at our convenience. Okay, so okay, fine. Next is the step for the scheduler and the optimizer and the scheduler. So here are my param optimizers. The parameters of the model. So we get the list of model.named parameters which are contained in param optimizer. Okay, and then we get the grouped parameters. So P for n comma P in param optimizer, and the grouped parameters. So we essentially get the optimizer here, where we have torch dot optim adam w, and we set the learning weight to be 1e minus 5. Okay, the training steps, we can calculate it to be an int, and this essentially will be len of the train sentence. Train sentence and config dot train batch size into, and it will run for config.epochs. So say for example, my train sentence, going back by the old example, if it is 30, right, the length of my train data text is essentially 30, then 30 divided by 2, 15, and config.epochs will be is 10, is set to be 10, so 15 into 10 is 150. Okay, that will be my number of training steps. Now we'll pass it on to the scheduler. So here we are using get linear schedule with warm-up. We'll pass on the optimizer that we have, the number of warm-up steps, and the number of training steps is what we just calculated from here, num train steps. Fine. So we are all set now, and we'll run it for the number of the epochs. So for epoch in range config.epochs model and comma train loss. So we'll pass it through the train function. We have train data loader, so it will be accepting train data loader, model optimizer, device, and the scheduler. So for each of the epoch, we will be essentially getting the train loss as well as the validation loss here. Okay, for each of the epochs. So we can see we started with the train epoch one. Train loss is 0.71, validation loss is 0.52, and we kept on going till epoch 10, where we have the train loss as 0.146 and validation loss is 0.152. Fine. Next, we'll quickly do the prediction function here. So def prediction, it will accept the test sentence, whatever sentence that we need to pass, model, and the level encoder, right? So test sentence, we will first do a word tokenize of it, okay, and then we will further encode it using the same tokenizer that we used for the purposes of training the model. So that's what we do in this step. And then we have the test data. Now we'll create a dataset class, test data, and test sentence, and tags would be essentially the one and to the length of test sentence. And the num tag we essentially would be having as len le dot classes. Okay, so that will be my number of tags. Fine. With the torch dot no grad, we do not need to calculate the gradient here, right? So with that's why we have torch dot no grad here. Data is equal to test dataset 0. Okay, for I comma z in data dot items, we have sent it to device and squeeze it 0. And here in the final step, we essentially uh, inverse transform the tag which have been encoded. earlier through the label encoder. Okay, so that was the step here. So then, in this particular line, so now we start doing the prediction. In fact, so we have the test sentence say as we have Argentina in the final of the World Cup. Today is what? Today is 18th of December, and it's the World Cup, the final match that's going to happen in a couple of hours. So let's see. We have Argentina in the final of the World Cup. Let's do the prediction on top of it, and it says that Argentina is the lock. The rest of the tokens they have been identified to be of class O. So which means that it works. It gives us the LOC. Our data was very minimal. So let's not expect a very high accuracy. We really need to have much more data in order to get some very decent result, right? The final step is if we want to save this model, right, whatever we did through the Tenipox, then we can do a torch.save model.static and model.min. We can essentially, in this case, Kaggle, which since I'm using Kaggle, in this case, it will reside in my output. Okay, so hope it gave you essentially a very quick walkthrough of the code that's involved into doing the NER tagging or NER predictions using the transformers. I hope you liked it. I will request you to pause the video and look very carefully through the code while going through it, right? So and that's a kind suggestion. And in the coming videos, we are going to cover the relation extraction and using essentially using refer and variable models. So thank you. Thanks very much for watching this video.